Okay, good afternoon, everyone, and welcome back to our final session of the workshop. So it's my pleasure to introduce our first speaker of the session, Marek Stastna. It's lovely to have you here, Marek. Over to you.
Okay, well, thanks to the organizer. Thanks to the speakers for the varied and interesting talks, and thanks to Magda for many years of lab and other forms of friendship, football and other things. So I'm going to tell you about internal waves. And I was thinking about what kind of stuff I wanted to talk about, and I thought I'd focus on shear because shear has some interesting theoretical puzzles. So what does this be like? How did this guy fund that? So that's how you fund that. Okay, so this is quite a famous picture. This is the fourth fjord up from Vancouver. I'm muted.
Just keep going.
Okay, it's called Knight Inlet. It's a famous site for oceanographic measurements. It's famous for kayaking, whitewater kayaking, because there's a lot of tidal rapids. So if you're a geography fan, right? So fjords tend to be sort of drowned valleys, right? When the sea level went up at the end of the last ice age. There's these leftover hills called glacial sills, like the one over here. So it's a very long ways. The ocean would be somewhere out over here. There's a river somewhere out over here. So there's a stratification with freshwater, sort of consistently overlying salty water. And then you've got a fairly strong tide because you're confined laterally and you go back and forth and back and forth. Okay, so this is a rather well-endowed expedition. I got this from Larry Army back when I was a postdoc, more or less to rub some salt in a wound, but that's another story. So they had a boat. That's the boat over here. They had money for a helicopter. That's why you see a picture of the boat. And then they saw the boat would see these sort of striations, right, in the surface wave. So modulations of surface wave structure, which are due to these suckers over here, these little lumps, which actually aren't that small. They're on the order of 10 meters tall, right? And so what you're seeing is backscatter off the different sort of layers of density. And this is sort of sitting over top of this undersea hill, right? And this is a case where the tide would be going from your left to your right, and these waves would be propagating against it, right? So if you want a weakly nonlinear analog, this is Grimshaw-Smythe, except of course this hill is way too large for that theory. So if you like nonlinearity, I'll point out that there's this beast over here, which I did some work on many years ago with Dick Pelche, but still sort of scares me, right? So there's all sorts of nonlinearity that I think we understand in the ocean, but not all of it. And this would be a particular example of that. Okay, so this is my world, stratified Navier-Stokes. I've color coded the different terms because I use this for teaching. Couple of interesting points, right? So put these two together and you get an elliptic equation. So basically, some people say it's a Lagrange multiplier problem, or an elliptic problem, even though it's got all this time-dependent stuff. Of course, you have no conserved quantities, right? If you have nu and kappa not being zero, even if you do set them zero, you've got 8. So Benjamin showed that. I think it was the early 80s. So you don't have infinitely many conserved quantities, even though you do get things that look like, where are they? KDV waves. There it is. Okay. So the model I use is SPINS. It was written by my former graduate student, Chris Subich. It's an open source pseudospectral code. It's really quite good. MPI parallelized. This is the webpage we have for it. It's also on GitHub so you can grab it if you need it. And this is the largest simulation we've ever done with it for reasons of Magda and I's past. It was a mode 2 wave by a fellow named David Deepwell. And you'll see sort of kind of the modus operandi for most of my work is that I like the aesthetic aspects of fluid mechanics. So this is a rotating system, which I won't talk about too much today. So there's some effects of curvature, right? So this mode 2 wave curves backwards. It's got these beautiful billows that end up being trapped near the wall, and then they break down into stratified turbulence. And this thing I think this was like on the order of 8,000 by 500 by 500. So quite a large simulation for about 4.5 years ago. So I want to talk about sort of things that are a bit closer to theory. It turns out mode 2 waves are a tiny bit complicated, but let me sort of set the stage for the background. So I like stratified fluids. I'm in particular like continuously stratified fluids. I think the next two speakers will tell you about layered fluids. So I think of a background stratification rho bar of Z set by this nice, C infinity function over here. And then this is the buoyancy frequency or the Brent-Weiss-Solid frequency squared, which is related to its derivative, right? And so you imagine you go to the lake on a nice summer day, you hop in, it's nice and warm at the top, and then you dive down and it gets cold awful quick, right? So for those of you from northern climates, it's a fairly common experience. So that transition, which would be over here, is called the thermocline or the picocline more generally, right? And it ends a waveguide. Okay, so here's an example of a fully nonlinear or exact solitary wave for this situation. And there's an interesting variable that kind of makes it possible to take all the field variables, right? Because you got velocity and pressure and density, and turn it into just one. So this thing's called the isopical displacement. So imagine you're sitting here at the wave crest, and you ask yourself, where or how high would I be if I kind of rode way out ahead of the wave to plus infinity or minus infinity? And that, right, so you'd be at Z over here, you're at Z minus eta. Eta is called the isopical displacement, and you can reformulate the stratified Euler equations, and I'll show you a little bit how, in terms of one equation for eta, okay? And then once you've got eta, then you can get everything back, right? Okay, so that's kind of that's the plan. Okay, so these are some very old simulations, just to remind you just how long we've been at it. This is from my thesis days back in the late 90s. This is stratified adjustment. This is kind of what Magda showed everybody in the lab. It's a numerical version, so instead of having a wall at one end, I kind of lump up some fluid in the middle. The stratification now changes in the bottom half, so I'm going to expect waves of elevation, which is actually what Magda had in the lab on Wednesday, and it's the thing that kind of looks like really, really long surface waves. I've set it so it's a total 100 meters deep, so I'm only showing you a part of the water column over here, and this axis is in meters as well. So you lump it up, you let it go, and if you just focus on the rightward propagating stuff, right, you get a rank order train of solitary waves. And the question is, right, how well can I describe these things? And the answer is going to be rather well. And then what I want to talk about today is how you break the symmetry a little bit, because in this case, the wave train going to the right and the wave train going to the left are the same. So if I include a linear background current, like we saw for surface waves earlier in the week, right, you break symmetry, and now the rightward propagating waves, the ones that are kind of going with the shear, end up being fairly sort of taller and thinner, and then the ones going the opposite direction end up being kind of broader, bell-like or something like that. Okay, and I'm going to give you a little more of the story of shear as we go along. Okay, so before I do that, just kind of remind you how you go from kind of the numerics-based world that I live in to the ones with the specialized equations that we've heard a lot of talks about. So what you do is you restrict yourself to 2D, you use the grad u equals 0 condition to introduce a stream function, you pose it a separable solution, a x comma t, phi of z, and then you do a bunch of algebra, and then at leading order, you get this equation, right? So this is the modal structure equation for the vertical, which is an eigenvalue problem, right? So you specify the wave number, you get c, right, the phase speed, and then if through a bunch of asymptotics, you would end up getting a KdV equation, a Gardner equation, a fully extended KdV as far as you want to go. Okay, and so this is the KdV, kind of the common way it's written down here, right? So the idea is that, well, this tells you the horizontal structure, and then I guess this is supposed to tell you the vertical structure, right? Okay, so here's a couple of examples of modes. So this is what happens when the wavelength is fairly long, right? So this is on a lab scale, and so sure enough, mode 1 ends up being this black curve over here. Mode 2, which I showed you a bit earlier, is the blue curve, and higher modes and so on. If you let the waves get shorter, right, this is kind of like a decay. If you think about it, right, if you covered this up, you just get kind of an exponential, right? So you see that you end up being more trapped near the pick and point, right? So if you're thinking about measurements and you wanted to do something like, say, shortwave, resonance, you're gonna have to measure to detect it much closer to the pick and point. So there's these little things theory tells you all along the way. Okay, so well, we've seen this a lot of times, right? People love the KdV because the KdV does beautiful stuff like this. Right, so this is a two salt-Hahn interaction. There's various flavors of it. I just kind of like this one because it looks pretty. The problem is, if you actually start carefully looking at that vertical structure, the story is much less nice. So this is an example of resonant generation back from my postdoc days. Came out in 2005. And what I do is I just extract a profile down through the crest of this wave. And the theory I'm about to show you, the Dubreil-Jacotin Long theory, is indistinguishable from that. But the weakly nonlinear theory fitted to the velocity at the bottom of the ship that you'd be measuring from up here is terrible. Okay, and there are ways you can fix it. There's something called Euler-Lagrange coordinates that works for certain kinds of stratifications, but for complex stratifications like the one John showed this morning of Norway, you can't win, right? So one of the biggest things that I, as a reviewer, get sort of fussed about is that whenever people present weakly nonlinear results for the ocean, they never seem to want to talk about the vertical, right? I mean, you also have phase errors in the horizontal. There's kind of a big, long, complicated theory, but the weakest aspect of all the KdV hierarchy is the vertical structure. okay, but it's such a pretty theory, so it also predicts a whole bunch of other things. So this is sort of related to what Dimitri talked about, right? So if you look at the Gardner equation, you can, instead of getting the taller and thinner type solitons, right, like you do with KDV, you get these things that tend to a limit. Sometimes they're called conjugate flow solutions, sometimes they're called tabletop. There's all sorts of names. So it's good. It's actually beautiful that it predicts this qualitatively, and it's worth doing just for that. However, if you're trying to justify to the funders that you want to do something quantitative, this picture again from that 2005 paper should give you some pause, right? So so to clear this up, this has changed names over my career many times, right? So this should be called the Gardner. So thanks for setting me straight, Dimitri. But I didn't have time to rework the caption. It's an old paper, I couldn't find it. Only had the PDF. Right, so here's the weakly nonlinear theory, and here's the conjugate flow, which ends up being kind of, you can test it in a numerical model, and ends up being exact, right? So when your stratification is near the mid depth, which is when the Gardner is supposed to work, the fit is awesome, right? But you get a little bit away, right? So 60% of the total depth, 70%. Now your predictions are awful. Okay, so the moral of the story, I think, has been some beautiful mathematics shown, right? There's nothing wrong with mathematics for the sake of qualitative things. But when you're trying to sell this, if you're saying it gives you quantitative predictions, you are most likely overselling. So just maybe be a little bit careful. Okay, so a little bit of math, right? So I love this equation because it makes a very, very different deal with the devil than the KDV. It says, okay, I don't care about all the solutions. I only care about solitary waves. Okay, so I'm going to shift into a frame moving with the wave, and I'm going to ask what structure it has, right? And I'm going to I've seen lots of beautiful mathematical tools this week. Here's a really simple one. You introduce a bilinear operator, the Jacobian operator AB, which looks like this, okay? And what you notice is that if the Jacobian of A and B equals 0, means that there's a functional dependence, okay? So that's kind of the big trick in deriving this equation. So then if you write down the density equation, you say, well, hold on here. In a frame moving with the wave, the density as a function of x and z is just the background density evaluated at the upstream height. Right, that's what this says. So rho bar is the upstream, and this is z minus eta, which is the upstream height. So the fundamental nonlinearity in the equation will come from this. Okay, so then the rest is just algebra. You plug it into this, you end up getting this expression. After a little bit of algebra, you say, aha. So unless I'm unstratified everywhere, right, this Jacobian's got to be equal to 0, which means these two quantities are not independent. So psi is a function of z minus eta, and then you ride one of the streamlines way upstream, and you say, what happens upstream, right? Well, if I'm moving with the wave, right, there has to be kind of a countercurrent with the wave speed. Okay, so that's what this expression is, and then that allows you to find what g is, and then a little bit of algebra says, aha, psi is c eta. So now you've got your velocities in terms of eta, or eta in terms of the velocities, right? And then you have to do the same thing, except with the vorticity equation, which, well, that doesn't fit on a nice slide. It's a lot of algebra, but I'll give you a source for it. And when you do all that, you end up getting this nonlinear elliptic eigenvalue problem called the Dubreil-Jacotin Long equation. And there's Madame Dubreil-Jacotin, who actually did this years before Long. Long did this for lab work in the 50s. Okay, so there's a sample solution. It's based on a direct variational method due to Turkington. And once you've got eta, you can recover everything. So this is kind of an oceanic stratification where you've got a main picnicline and then some stratification underneath. Okay, so there's a variety of implementations available for this. Kevin Lamb has one in C. In 2011, as a class project for me, actually, Mike Dunphy wrote a version in MATLAB, and he's got it on GitHub. And there's one in Python as well. And the upshot is that you can get these exact solutions in less than a minute on a laptop. So not expensive, not something that's got a huge cost. So what can you do with that? Well, you can do old school stuff. So this is from Lam and Wan, from Kevin Lam's sort of fundamental work on this stuff about these waves with flat crests. But you can do some slightly more modern things. This was Will Zhu's work towards the end of his PhD. He chose one of these big waves and calculated it so that enhanced shear waves sort of serves as an amplifier and generates these billows at the back, right? So you need a fairly exacting set of boundary conditions for this to come out clean, and the DJL lets you do that. Okay, and Will was a bit of a wizard at graphics as well. Okay, well, you can do other things, right? You could say, well, okay, so we've talked a lot about these sort of solutions, which there's a central peak with superimposed with some periodic stuff, right? So how does it turns out that this thing, which is basically baroclinic vortex propagating along, takes these waves, and because of the shear between the blue and the red, kind of rips them apart. Okay, so this is before the wave packet interacts, after, during and after, and you can see, and this is just the wave packet by itself, which more or less survived for this time, but the wave effectively killed it. Okay, so those beautiful breathers probably need constituent longer waves, right? Because if they were short waves, that middle part, right, the wave would change the kind of the environmental conditions and effectively destroy it. This was an earlier paper from Will's thesis days. Okay, so that's nobody read that paper, I don't think, but people have seen this one. This is the Taylor-Goldstein equation. This is the way shear shows up in a linear theory, right? So this is the vertical structure equation, ODE, right? And you've got this thing over here and over here as well, okay? And going back to Kelvin, right? People notice that something bad happens if U of Z equals C somewhere, and then when you fix it, is you get these Kelvin's cat's eyes patterns. So I've been looking for these in simulations for a long time as well. Turns out they're not quite as easy to generate when you've got a wave as can be, but it is in almost every textbook. Okay. So this is back to my thesis days where I extended the DJL to include shear, monster amount of algebra, stupid amount of variational analysis. But what you do is you can't prove the same convergence theorems, but you can get the algorithm to work. So these are maximum amplitudes of waves with a linear shear as the strength of the linear shear increases. It's all been non-dimensionalized. Okay. And here's the sort of picture of what's going on, okay? If you have a strong enough shear, right, you get two wave trains, one going to the right to the left, but the one going to the right is largely undisturbed, but the one going to the left now wants to switch polarity, right? So you want to go from waves of this polarity to waves of this polarity, so it breaks down into a wave train instead of a train of solitary waves, okay? So I thought that was at the time, that still gets quoted because I think that's a pretty funky result, okay? So yes, shear could just modify the characteristics of your waves, but it could also modify your wave in a rather fundamental way that it wants to not be a solitary wave, which is nice. Okay. So then many years went by and I decided, well, we should revisit this. And I'll show you why, but let me first show you what I did. Okay. So this is our pseudospectral model, very large 2D simulations on the order of tens of thousands of points. And then kind of a near surface shear profile, right? The background velocity profile. And let's see what happens, okay? So I varied the strength, and it turns out that not only are there instances where the shear is strong enough to break the linear theory, which I think is no surprise, it also breaks the DJL. It just doesn't converge, right? The variational algorithm wanders and wanders and wanders and eventually just breaks, okay? But when you run it, you still get wave trains, which is super interesting, right? So this one actually works okay. This one's going against the shear, right? That one's always been relatively well behaved. Okay, but this one, there seems to be a change in wave shape, right? So the wave is kind of a little more pointier, and then something seems to be happening up here. Okay, there's a whole bunch of stuff seems to break down. So you sort of start to think to yourself, well, is it like those cat's eyes patterns or something like that? And these are quite well resolved. So where am I?
So when you say strong shear, what's the speed of the current compared to linear?
Well, it'll be bigger than the linear wave speed.
So what is strong?
I guess I would say 1.25 times of the linear propagation speed or so. I mean, I vary it, right? So it's sort of hard to say. It's a great question because the actual quantity is emergent, right? It'll depend on what your stratification is. So you want to add a second picnic line or some weak stratification at the bottom, you'd have to recalculate it. But 1 1/4 is a decent heuristic. Okay. Right. So here it is again, that same figure. And then here's the detail, right? So I take the top 2 meters and I blow it up and bit of a surprise, right? So you get regions which seem to have closed streamlines. These are lines of constant density, but you can take them as proxy for streamlines, right? There seems to be a loss of order and then kind of something that looks like, if you close your good eye a little bit like that Kelvin's cat's eye pattern back here, okay? So that was 2018. Turns out completely independently in my own group, a graduate student working with Kevin Lamb was working on something called subsurface cores. And the idea is that you can continue the solutions of the DJL equation and get these things working completely separately. It turns out these things happen out there. So the hypothesis is when shear is strong, right, you get a new kind of wave, which is more or less a vortex, right? You can see it sorry, I keep losing this over here, okay, right? And then everything is kind of the isopicals get wrapped around that vortex, which is my hypothesis of why the detail doesn't work for this case. So why did I do this? I did this because years before that, I helped out a fellow named Ryan Walter with his thesis at Stanford, and he did a bunch of measurements. So this is Monterey Bay, right? So San Francisco is somewhere up here. And it's a really complicated system because you've got the coastal mountains, right? Santa Cruz would be somewhere along here. And you're modulated by winds. And what he found was that in some days when there's a wind shadow, the front kind of moved past his measuring site and broke down into this rather beautiful, what looks like a solitary or dispersive wave. What did you guys call it? DSW, right? Yeah. So something like that, okay? And for the life of me, Ryan and I tried for almost a year, we couldn't get linear theory or nonlinear waves to work for this. Luckily, it was a field oceanography thesis, so we kind of got away with publishing it. We published in Continental Shelf Research after some work, but it bothered me for years, and so I came back to it. So my hypothesis is that in these situations, the wind drives these strong currents, and that changes things as far as kind of the theoretical ability of tiny little humans to describe these waves. Okay. So hold on, it's coming. Okay, so right. So then how do oceanographers do that, right? So John talked a little bit about different kinds of ocean models, right? So most ocean models don't actually bother with non-hydrostatic cases, right? And so the MIT GCM is one of the ones that can. And in particular, it has a fairly standard parametrization for what wind does. So if you think about what wind does, it generates surface waves, right? Creates a whole bunch of turbulence, and that deepens the mixed layer, okay? And so one of the fundamental parameterization called the KPP parameterization takes whatever scalar you're interested in and transports it to the bottom, right at the top of that mixed layer. So it's called a non-local parameterization because it's not just eddy viscosity, okay? So there are other models that implement this, but we decided to try the MIT GCM. So this is Chi-Chi Zhu's master's work, okay? So she sort of set it up like this. She starts with a DJL equation and then lets the wind blow, right? Turns on the KPP scheme and allows this shear to develop. And the question is what happens, okay? So here's her parameters, right? So the MIT GCM, you know, it's not quite as fast as the pseudospectral model I was showing you. So what she can afford is 600 meters deep, so kind of off the shelf, right? 40 kilometers across, 4 hours of simulation time, and then the rest of the stuff comes along there. But the key part of all this stuff is that she actually doesn't do that much for background viscosity and diffusivity. She sets it to 10⁻⁵, which is a lot lower than most studies with the MIT GCM, but she keeps this on, okay, this magical parametrization. And when she does that, what she ends up getting, so here's if you like details, this is the detail of the KPP. Okay, and this is a fairly standard article. There's a better and more modern review of this, but this is the standard article on it. So what happens, right, is you get this kind of near surface shear, right? And if you don't do the KPP, it ends up just sitting in the very, very top of your model and basically crashes your code. And the KPP smears it out a little bit, makes it a little more realistic. And what ends up happening is that you get an adjustment, right, at first. Okay, so this is the junky run without the KPP. And with the KPP, you shed a bunch of waves. And you have an adjustment, okay, where everything seems to look okay. And if you look at the details of what happens, you actually develop one of these subsurface cores. So in white are the regions where the velocities are larger than the estimated propagation speed, right? So that's the parts that it's effectively breaking, right? So actually, your question is harder to answer than this, right? Because the actual propagation speed, right, which you don't know ahead of time, you can just estimate it from the data, and then you can say, where are my velocities bigger than it? But the linear theory, you know, the background state is changing as well, so you have to recalculate it all the time. Anyway, she did some nice work, and so she sort of shows that the core thickness increases over about the first half an hour of the wind whipping up, and then depending on how strong the wind was, you know, you get a subsequent decay.
Interrupt. Are you sure that U larger than C, maybe a bit larger, but can it be very much larger? What we saw in experiments where we have this platform, where we have surface and so on, is that U is comparable to C, but it breaks.
Yeah, well, okay, that's a so my why I don't trust it. Maybe can I just table it? I'll answer it. But let me finish the story, and I'll have that. That's a good point, John, and I'll tell you what I think about that when I put some stuff up. just to finish up to do her some justice. Okay, so then if you put it the other way, very similar things happen, but you just kind of get this blunted shear profile down the middle, and then the density is more or less the same, right? So I guess to get back to John's question, yeah, these cores aren't very big. They're not terribly well resolved, right? Because you're paying the price to resolve 600 meters depth, right? So it could be, and they're not 3D. So if it was 3D, your lab work always was, right? So maybe it would break down and everything, basically you get this region where U is approximately C, which is what I think should happen eventually.
Yeah.
To the extent that the MIT GCM can do that, I'm not too sure. Okay, so to summarize, I've got a bit of a coda just for fun, but just to summarize. So here's what I think is known about shear, and here's what's not known, right? So in blue, what's known, the background shear can change the detailed distribution of density and momentum in an internal solitary wave. The background shear can change the upper bound on solitary amplitude. So I showed you that it can change polarity, but you can actually show as well that you can go from tabletop solitons to waves that are breaking and vice versa. You can go to cases where you get sort of nominal shear instability, where your variational algorithm starts to wander and stuff like that. Okay. Background shear can preclude solutions to both weakly nonlinear theory and fully nonlinear theory. So it'll disrupt your vertical structure of your weakly nonlinear theory first, but it'll eventually kill the DJL too. Okay. And then background shear also leads to an interesting novel combination of wave and vortex, right? So going back to this long time ago, Peter Baines reviewed one of my articles, and made me read way too much for one article, but it was really interesting. So he has this notion, because I guess old school physicists do this sort of stuff, that you need resonance for every instability. So he claims that shear instability is resonance between vorticity waves and gravity waves, right? I'm a nonlinear waves guy, so I don't tend to think of needing to need tiny little waves to resonate with one another. But it is certainly possible that the reason the DJL doesn't work is because it's a gravity wave descriptor, right? So if you started with, I don't know, a generalization of Lamb-Chapligan, right? And you start with a vortex and then you wrap some stratification around it, maybe that's the way to get this other branch of solutions, but I don't know how to do that yet. Okay, so that's the first point of things we don't know, right? How does subsurface go 3D? There's some preliminary work out of Pete Dempsey's group at Cornell. There's a lot more that needs to be done. Does it end up like John's old experiments for breaking waves, which didn't have shear, right? And then if you care about practical things, right, what is the best way to represent changes in the background state in field scale simulations? So what Chichi did, it looks really simple, but somehow nobody's bothered to do it, right? No one's bothered to do this simple traditional problem with this sort of scheme that many of the oceanographers use, okay? And then finally, can the KPP-based predictions reported in this talk be confirmed in the field? Okay, so I think I've got 3 minutes left, so let's leave it there. No coda, yeah.
I'm very much for an interesting talk.
Question about absolutely not knowing much about this field. So what exactly you doing with this KPP? Is that you just insert the results of this KPP for given background shear, or it's kind of time dependent? You insert this in time dependent.
Oh, yeah, okay, that's a good question. Yeah, sorry, I went too fast. Okay, so what you do is you do the stratified adjustment problem. So it's 0, it looks just like everything else. It's just that when you now you impose a wind at the surface, and now you're saying how that momentum is redistributed in the water column is according to the KPP. So the KPP, actually, good thing I put this up,
But
has
it's a function of time. You take it. No, it depends on time.
Yeah, it's a time yeah, the MIT GCM is a time dependent model, but it is this is a little weird, right? Because this thing is what gives you your traditional eddy viscosity, but this is that non-local term, right? Stuff gets a free ride from the surface to the base of the mixed layer. So.
Yeah, thank you. What struck me with the field measurements I presented was that the Kelvin-Helmholtz instability or stability always appears in the front of the wave. And that occurs even the amplitude is not very big, but the wave is very long. In your computations, it starts maybe in the middle of the wave, but it's visible in the back part of the wave.
Yeah.
I think you will be able to play with this code. You could squeeze the thermocline or picocline, and you could make an even longer wave to see if you could move the braking to the front.
We did do that. You can do it. There was a paper, so Carl Helfrich and postdoc, whose name I forget, did this. They did kind of a variational version of kind of the best perturbation to trigger these. But my idea is always like, hey, if it happens naturally, that's the best. So I just add noise and let it go. But you're right, it needs space. It's a spatially growing shear instability, so it needs space to grow. I have gotten it to go to about here by doing exactly what you described, by thinning out the picnic line and adding more points. But I'm not aware of any studies where it'll happen here.
Because I checked that now, it's in the weak case, it starts in the top.
Okay, well, we got a puzzle.
So I'm surprised.
Yeah, okay.
I'm surprised.
And for, sorry, just one more while recording, from sound setup, you don't have recording? And sorry, let me see the hands again. Yes, please, yes, thank you. Alex, you can talk in the break. Yeah, sorry.
Oh, sorry, okay, yeah, so you demonstrated that the KDV is not a good fit for lots of phenomena we're trying to capture. What about some of these other models, like asymptotic models, like intermediate long wave equation?
So yeah, so that one's been done, the BO's been done, it never really gets better. I reviewed something where they try to use Roberto's models, but it wasn't very good. So what you'd like to do is you'd like to take the models that have the strong nonlinearity and compare those against DJL. So that the thing is, and actually John and I had a exchange over a review that he did of one of my papers. There's kind of a disparate literature, right? The layered literature and the continuously stratified, that's the right way to answer your question. And you try telling that to a funding agency, you'll get a big old kick in the arse. So, yeah, someone's got to do it.
The KDV is the best.
Extended KDV. This shows them
The KDV is
Okay,
full extended. not just-
which one's that with the two? So Lam and Yan, okay, so I guess there'll be a new paper on this. Lam and Yan, like 96, has them going up for bores. It was JPO, so respectable source. Anyway, I should let it go.
Thank
Thanks.
you. Thank you very much.